Seems these days we need too much technical assistance for everything. All right, so today my plan is actually to go a little bit faster so I can cover sort of 2 lectures in one, because we have already discussed about many different aspects of elimination. And I suppose you guys read everything about the elimination matrices from lecture 5, correct? Yes, or it was lecture 4? Lecture 4, all right. So actually today is lecture 5. Okay, so I'm going to be doing a little bit of jumping on the slides, but nothing significant. So I'm going to start talking about matrix elimination. And all right, so let me summarize actually the first half of the lecture. So I'm going to put all of these things up. And in principle, everything today is going to be those 4 bullets. We're going to take a matrix A. And we're going to start with rectangular matrices, but we would generalize this and try with row operations, right, using these elementary matrices that you read on lecture 4 to bring that matrix A to a form that is an upper triangular form U. Okay, so that's the first major task. And then if we manage to do this, we will see that we can solve equations like AX equal B in a very simple manner using what's called back substitution. Also, I'm going to emphasize, as part of the elimination process, is we're going to factor, or we're going to write, if you like, A as the product of a lower triangular matrix times an upper triangular matrix. So this is, unless you heard already about this is sort of your first major decomposition of a matrix to 2 simpler matrices, one lower triangular and one upper triangular. And actually, at the end of the day, this decomposition A equal LU is way more significant than the elimination process, okay? Actually, most probably in practice, you will never use the elimination process directly. You would use the LU decomposition. Okay. Let me just start with a trivial example without elimination matrices. And once we understand this, with this example, we can generalize using the notation from lecture 4. So let's say that we have this system of equations. A is given by this nice matrix here. Okay, B is this vector. And we want to solve the system of equations AX equal B. So the first thing I'm going to do, I'm going to start doing row operations on the matrix A, but because I want to solve AX equal to B, I'm going to combine A and B together in one new matrix that I call it the augmented matrix. So think of next to A, you put the column of B, and you think of this as a new matrix. So effectively, whatever operations I do on A, I'm going to do them also on the vector B. I have to, right? I mean, to be consistent, you're not going to start adding rows without doing the same operations on B. So I'm going to do this simultaneously by defining what's called this augmented matrix. And sometimes you will see this vertical line and remind you where B is, all right? But sometimes it's defined basically from the context of the particular slide. All right, so let me take this matrix A that we had here, take this vector B and define it as an augmented matrix. This is my matrix A, and this is my vector B. And I'm going to start doing what is called the elimination. The objective is to make this matrix to look, at least the matrix A, to look upper triangular. So if we're going to make this upper triangular, we need to get rid of anything below the diagonal. So we need to get rid of 3, and we need to get rid of 4, whatever it is. All right? And how are we going to get rid of them? By somehow taking linear combinations of rows. And here's the procedure. First, we're not going to touch row 1. And the first element in the diagonal of row 1, we call it the first pivot element. Okay? Very elementary. You have seen this before, the first pivot element. So what I'm going to do is I'm going to try to get rid of that number 3 there. And to get rid of 3, I'm going to define what's called a multiplier, which is the ratio of 3 by 1. So if you take the element 3 and you divide with the first pivot element, you get a multiplier which is 3. So what I'm going to do is I am going to subtract from row 2 3 times row 1. Will that get rid for me that element 3? So if I subtract from row 2 3 times row 1, will I be able to get rid of 3? Can you see that? Yes? Yes, okay. Take 3 times row 1 and subtract it from row 2. So 3 and 3 will cancel. 8 minus 6 will give me 2 there, all right? And then 1 minus 3, can you see the minus 3 there? Because I multiply row 1 with what? We multiply row 1 by what? 3. So 1 minus 3 gives me minus 2, and I do the same thing on the right-hand side. So 12 minus 3 times 2, it gives me 6, okay? And so I got rid of that 3. Now, in principle, you will also have to get rid of whatever it is below 3, because we want progressively to make this matrix to be an upper triangular, but there is nothing in this example to get rid because there is already a 0, so we're not going to do anything with that 0. We are going to leave it as is. What's the next step now? What should we get rid? 4. Everybody agrees we need to get rid of that 4? All right, okay, so I can go fast. Can you tell me what is the multiplier to get rid of 4? 2. So we're going to subtract 2 times row 2 from row 3. We agree? All right, 2 times row 2 from row 3. So if we do this, somewhere on the next slide is going to lead us to this beautiful matrix that you see there, that immediately you notice it's upper triangular and we're done. And the 3 elements that you see there in the diagonal are what we call the pivot elements that luckily in this example come not to be 0. Okay? And if the pivot elements don't come to be 0, means that this matrix is invertible. As a matter of fact, if you have an upper triangular matrix, okay, what is the determinant of a matrix? I have not said anything about determinants, but since you know, you're ahead of me. If you have an upper triangular matrix and you want to compute the determinant, what's the determinant? In any way you calculate your determinant, what is the determinant of an upper triangular matrix? The product of the diagonals. So if we do this decomposition here, we actually have computed directly the determinant because it's the product of 1, 2, and 5, which are the pivot elements. All right, so we get that as a free bonus, if you like. We can get the determinant, but really, we don't know what determinant is because I haven't defined it. So it's that hypothetical quantity you learn in high school. Okay, there is U. So basically, we transform the matrix A to an upper triangular matrix that I call this matrix U. This is the vector C, which we did the same operations on the vector B that we did on the matrix A, and that results on a matrix C. And so effectively, the system of equations AX equal to B has been transformed to UX equal to C. All right? So C and U are the new names I use. U, upper triangular, and C is the vector that results by doing these operations on the vector B. Okay, so can you tell me, is it easy to actually solve now UX equal to C? Is it easier than solving AX equal to B? Look at UX equal to C. What will be, on this system of equations here, what will be the way to solve it in the computer? Look at the structure. How would you do it? What is the word that goes with it? Must be written on the slide also. How would you solve this fast in the computer, this system of equations? Can you solve it sequentially? Look at that. Z, 5 times Z equal minus 10. So what is Z? Minus 2. if you know z, can you use the second equation, 2y minus 2z equal to 6 to compute y? So you can start from the bottom and go up, and this method is called back substitution. So you can solve this method with back substitution, which is way cheaper than actually any other method in solving AX equal to B. So, so basically this process of elimination of transforming the matrix A to an upper triangular, it really, at the end of the day, it serves the need to actually solve for the system of equations, and the system of equations being having a matrix that is upper triangular. It's a very simple system of equations that actually we will see what the cost is, but is substantially less than solving the original AX equal to B. Okay, without putting the slide up, you remember what we did with elimination. We started with the first row, and we said the first diagonal element is the pivot, and then we got rid of the elements below the first pivot element by doing elimination. And then we did the same thing in the, we look where the second pivot is, and we got rid of things below that. So when is elimination going to fail? Can you think a situation where things will fail? I don't want in technical terms, I want with numbers. So I do these operations, right? For what, what will you be seeing there and say, ooh, I cannot proceed. One of the pivots is 0, right? Because you remember to define the multiplier, what did we do? Right, for each row, we took, the number that we want to get rid, and we divide it by the previous pivot. So if the pivot is 0, we are in trouble. Now, if the pivot number is 0, is there any way out of it? So if the first row, let's say, the element A11 in our matrix is 0, how do you do elimination? Do you give up? Do you say, that's it, I cannot do anything? So if A11 is 0, what do you do? I don't hear anything, The older you get, the less you hear.
Switch the rows.
Switch the rows, thank you. All right, so you exchange rows. So effectively, if you can exchange rows, maybe you can solve this problem. But if it happens that one pivot is 0 and everything below that pivot is also 0, then you're doomed, right? To exchange with what, okay? And we will actually see examples that they are like that. Let me be sure that I don't tell you slides I don't supposed to tell you today. All right, so we're okay until slide 26. So I'm going to bypass all of these things. So I'm going to actually now try to do elimination with matrices so we can see things a little bit more formally. So you went through lecture 4, and you know what the elimination matrices or these elementary matrices are. So we're looking back at the same matrix A. So here is my matrix A. All right, the second matrix here is the original matrix A. And remember, the objective is to get rid, to start with, of the number 3 below the first pivot. We want to get rid of the number 3. And you told me to get rid of 3, what I need to do is compute the multiplier, which is how much is the multiplier in this case? It's 3. So I need to subtract 3 times row 1, 3 times row 1 from row 2. And I'm claiming I can do this by multiplying this matrix A with this elimination matrix that you see up there. All right? And the way that when you studied lecture 4, the way you look at that elimination matrix, you look at the effect of each row in that elimination matrix to the matrix A. And when you multiply a row vector with a matrix, what do? What is the buzzword there? You take combinations of what? A row vector with a matrix, the row vector being on the left. The resulting vector is a combination of, from lecture 4, a row vector times a matrix gives you combinations of, nope, a row vector, think, a row vector times a matrix gives you combinations of, think of the matrix as row 1, row 2, row 3, and then the row vector. Combination of the rows. I mean, if it's not columns, it has to be the rows. So a row vector times a matrix gives you combinations of the rows. So when I multiply with 1, 0, 0, this matrix, I am going to take combination of the rows, but because there are 2 zeros there, it says, no, just use the row 1. Correct? So don't do anything to row 1. So the first row that you see doesn't change. 1, 2, 1 doesn't change because here there is 1, 0, 0. How about the second row times the matrix A? It says minus 3, 1, and 0, the elements. So the new row vector will have what? Minus 3 times row 1 plus row 2 plus 0, row 3, which is what we did for elimination. And how about the third row? It says it's a combination, but don't use the row 1, don't use row 2. Only take the row 3, which means row 3 remains exactly as is, which is 0, 4, and 1. Make sense? A little bit? I posted this extra lecture for, right, because I really want you to understand that multiplying a matrix on the right with a column vector, you get a combination of what? Of columns. And multiplying with a row vector on the left, you get linear combination of rows. Has to mentally, and visually, you have to sort of understand why is that the case. So what I have done here is I put all of this together in one matrix, which is this elimination matrix. And I'm actually, because we're trying to get rid of that 3, I am calling this elimination matrix E21. So what do the subscripts you think will mean? I'm going to put, I'm going to name this matrix elimination matrix with subscripts 2, 1. So that way I remind myself that this elimination matrix, what does it do? It eliminates which element? The element 2, 1. All right, so I'm going to call it E21. That's it. OK, all right. Can you tell me, so what is my next elimination matrix going to be? And what name should we give it to it? What did we say we need to get rid next? There is 0 there. So we are not going to bother with the second 0 in the first row. So we're going to get rid of 4. So what elimination matrix should we use? E3. What subscripts? E3 what? 2, thank you. E3, 2. So, and what is E3, 2? You remember you told me before the multiplier is 2. So I'm going to have to subtract 2 times row 2 from row 3. So I put a minus 2 there. Very convenient, right? And then what you get basically your upper triangular matrix U. Now, trust me, the computer doesn't do calculations like this, right? This is for us, for the class. Okay, just so I can harass you with some elementary things. The computer doesn't have time to operate things that they are otherwise very simple, okay? We make them to look complicated by having matrices and all of these things. But there is something to learn by doing this type of things, so we have to learn first before we use computers. All right, so effectively, we had the matrix A. We first multiplied with an elimination matrix E21, then we multiplied with E32. And what is the result of this multiplication? What is the symbol we use for the resulting matrix? So what matrix do we get when we do these 2 multiplications and we finish? We get an upper triangular. How did we denote it, that matrix? U, thank you. So we denote this matrix as U, all right? So that's my matrix U there. And again, pay attention that in general, the elimination will look like that for a 3 by 3 matrix, right? After you eliminate element 2, 1, you will eliminate element 3, 1, and then 3, 2. But in our case, there was no element 3, 1. It was already 0. So really, this elimination matrix is the identity matrix. OK, so just to convince you that if you do elimination, you really solve the original system of equations. And you can see this with a simple equation here. So remember, we started with AX equal to B. We agree? AX equal to B. So we multiply with this elimination matrices, and I write their product as a matrix C, so I don't have to carry all of them together. So we multiply basically AX with C, we multiply B with C. E times A became U, And then on the right-hand side, we had this vector C that we did before, okay? So what I want you to concentrate is, effectively what we do is, we calculate an x that solves this equation, ux equal to this vector C there, E times B. Or equivalently, we calculate an x that solves this equal to that. Will you agree with me that the x that you will get will be actually the x of the original problem? Somewhere there was a theorem in your slides on lecture 4 that says that this thing, in principle, is identical to this. This is identical to that. Can you tell me what, to be able to say, oh, E cancels, sort of like if it was a scalar, and say, if EAX equal to EB, AX has to be equal to B, what is the requirement for that to be true? I told you when you have multiplications of matrices, you never do cancellation unless it's invertible. Thank you. There was one theorem there with products, and is this elimination matrices invertible? We haven't said anything, but as we will see shortly, the answer is yes. If they were not invertible, you cannot actually, the two systems will have different equations. I mean, different solutions, okay? So effectively, we haven't really changed anything. We're still solving AX equal to B, but we are solving it through a simpler system that has exactly the same solution. Okay. So let me actually, since talking about invertible, let me just tell you how trivial the inverse of the elimination matrix looks like. So can somebody remind me with words, what did we do on this elimination matrix? We subtracted 3 times row 1 from row 2. So what does the inverse should do? So if the elimination matrix subtracts 3 times row 1 from row 2, the inverse of that matrix has to reverse that. So it has to do what? Add 3 times row 1 to row 2. And how will that look like? It will look like this, where instead of -3, this is 3. And remind me, what is the number 3? From where the number 3 came? What name did we give to 3? Multiplier. So actually, the inverse of this matrix is very nice, because effectively, in that location, the only thing we have to go to do is put the multiplier, all right? And the rest, basically, okay? So I hope I have not done a typo here, right? Is this, let me just go backwards 1 second. Okay, so obviously, all right, so I'm looking here, right? 1, 0, 0, we did not touch row 1, we did not touch row 3, -3, 1, 0. So I can see a typo somewhere, let me see. No, actually, you know what? Come on. Yeah, so you see the typo? You don't see anything wrong? The first row, thank you. So as soon as I go back, I'm going to correct it, so those who listen to the lecture, that we have on the web, that we have the revised slides. Okay, so there's a small typo there. All right, hopefully it's corrected on the following up slides. So let me, since I mentioned in the beginning that, once in a while, we may have to do row exchanges because a pivot element may be 0, all right? So let's see how this thing will work with row exchanges. And I'm going to do this example very fast because there is really nothing else new here. Notice, so this system of equations, it looks a little bit weird because it's overspecified. I have 4 equations with 3 unknowns, all right? So elimination doesn't really care if it's a square, if it's a rectangular matrix, you know. It starts doing things, and at the end, you will decide if there is a solution or not, and hopefully we will have some time to see this today or on Friday. So we're going to do elimination, and the first thing we're going to eliminate, so let me just go here. This is my first pivot element 1, so we're going to get rid of that -1. to get rid of 20. Can you tell me the two multipliers to get rid of those two things? So for the row 2 to get rid of that, what multiplier I need to have? I'm going to need to subtract from row 2, row 1. So how much of row 1 do I subtract? -1, okay? And similarly for this element, I'm going to subtract minus 20. I'm sorry, I'm going to subtract 20, okay? All right, so when you do this, and you go to the next step, here's what you get. The second row becomes actually 0, 0, 0, 0. All right, so when you do the elimination, the whole second row disappears. So what do we do next? We cannot continue like that. We have to do something else now. So what should we do? Put this equation on the bottom, all right? And put the third row and fourth row as second and third row on the system of equations. So effectively what we need to do is we need to do what you see here. So the equation with the zeros, okay, we put it on the bottom, and the other two equations are there. And now my second pivot is 10 in the diagonal, so I have to get rid of 30. So I need to multiply row 2 with what multiplier? 3, all right? And if we do this, we will get our upper triangular matrix. Now, before I continue, let me just say something, and we will see this explicitly in the notes later on. When we, elimination in the second row gave us this 0, 0, 0, somehow we were very lucky. And you know why we were very lucky? Not because these things came to be zeros, but because the right-hand side also came to be 0. Had no reason to be 0. If it was not 0, then what would you have said? If that 0 during elimination came to be 10, then what do we say? We don't recalculate anything. We give up. We say, that's it. We give up. And what does it mean we give up? There is no solution. That's it. Okay? So in this case, we were lucky that this thing came to 0, but you know, you will see that may not happen all the time. Okay. So you know, the system of equations is like that. And effectively, what you really need to solve is a system of 3 equations with 3 unknowns. So originally it looked overspecified, but because the last row gave us 0 equal to 0, I can solve 3 equations with 3 unknowns with back substitution, and basically we are done with this problem. All right, I don't need this. So let me, I need to go. So let me go back to this LU factorization. I haven't really said anything about L yet. We said how we do factorization. We multiply with the metric C, and eventually we get a U, but we haven't said anything about this LU factorization. So let me go and do an example, okay? Again, doing the same things, but now I'm going to introduce this metric cell. So we want to solve this simple 3x3 system of equations that you see here, and we're going to use elimination matrices. And again, I think, is this the same system as before? I don't remember now, okay? So it doesn't matter. We will need to get rid of that 4 there. So we are going, the multiplier is 2, so we're going to put a -2 there. So E21 is like that. And so we multiply with E21, and we get rid of the 4. And you notice there, I get a 0, right? That's what elimination does. When you multiply with this E21, you will basically get rid of that element 4 below the pivot number 2, and we get a 0 there, okay? Then we're going to have to multiply with another elimination matrix to get rid -2. What's the name of that elimination matrix? E with what subscripts? 3, 1. So we're going to multiply with E31. Where is E31? And the pivot, you can see here, the pivot is -1. So we're going to have to put here minus the -1 is 1. Okay? So that's my elimination matrix. you multiply, you get rid of that element there. I see a 0, right? I see a 0. And what element next we get rid? We will get rid of that 1 in row 3, column 2. And the elimination matrix will be E3, E32. So E32 is like this. And eventually, we're done. Now, so if I put all of this together, I multiply E times A, where E is, what is E? Is E21, then E31, and then E32. And the order is extremely important. You remember, you cannot play around with matrices and change the order. First, we multiply with E21, then with E31, and then E32. So effectively, EA equal to U. E is this matrix. So I can write this equation as A equal the inverse of this matrix, all right? The inverse of this matrix times U. And the inverse of a product, remember, you reverse the order. You remember that nice thing? So the inverse of this will be the inverse of 2, 1, the inverse of 3, 1, and the inverse of 3, 2 in a reverse order times U. So the question is now, what is this wonderful matrix that has the product of the inverses of these elimination matrices? And how does it look? Can we even guess it? And you will see that that resulting matrix is way simpler than the matrices C. Way simpler. All right, so in principle, we don't really need E. We will need actually more the inverses of E. So let's see, I remind you, okay, you can actually test it. I don't have to remind you anything. If E21 is like that, that's the correct form. Actually, I see looks correct, right? E21 is like that. The inverse, instead of 2, has -2. So you remember on the inverse, what do we put below the diagonal? Where we do the elimination, we put exactly the number of the multiplier. And the multiplier was -2. The multiplier was -2, okay? So this is the multiplier. So effectively, the inverse of each of these matrices looks like a unit diagonal matrix. And in that location where we do the elimination, we put the multiplier, -2. The question now is, but what happens when I multiply all of them together? Do I have to do the multiplication in the computer? Or there is a magic somehow that the formula looks so trivial that I can write it down? So let's see. Let me first tell you why multiplying the matrices C is not nice. All right? Multiplying the matrix C is not nice. And I'm going to do this with this particular example. You remember we use E21, which is this matrix, E31, which is this matrix, and then E32, which is this matrix. And you can see in bold, you know, when you go home and you look at the notes, you will see minus the multipliers in the bold letters. So when you multiply all these three matrices, what do you get is you get this unit matrix, 1, 1, 1. You get minus the multiplier, so you get -2, you get -1. But look at that weird element. You get some weird number there that has nothing to do with multipliers. So in that location, somehow you got some number. There is no way you can guess it unless you do the multiplication. That's bad. And you know why this number came to be like that? Can anybody guess? When you do elimination, right? So let's say you eliminate the element alpha 2, 1, and then you go to eliminate alpha 3, 1. When you're trying to eliminate alpha 3, 1, to what matrix do you apply the elimination? You don't apply to the original matrix A. You apply to that intermediate matrix that you have computed after the first elimination. And because of that reason, that's why you get this weird number there that there is no way you can guess it. So the elimination matrices are not good for you, okay, in that sense. However, let's see the miracle of algebra, of linear algebra. If you compute the inverse of these products of the elimination matrices, and you do the multiplication because you don't trust me, you get this wonderful matrix that is there. And I want you to look at it and tell me what is that matrix looks like. It's the unit matrix, and then below the diagonals, what do you have? Exactly. What is 2? What is precisely 2 on our problem? What was 2? The multiplier. What was -1? Our multiplier. What was this other one there, the other bold in location 3, 2? Our multiplier. So basically, you take your unit matrix, you put below the diagonal the multipliers. That's the matrix cell. Done. There is no other weird numbers coming. And you may say, wait a second, you told us before that because I do eliminations on matrices that already have changed, it's not anymore A, I get this weird 3. And why it is not happening with L, I'm going to give you a little proof, since you like proofs, right? I mean, your spirit should be, I don't trust you anything you say unless you prove it. Right? I mean, why, you know, I can tell you it's magic, but it's not magic. So let me show you a trivial proof of this, okay? So here's a trivial proof. Let me go back. I'm gonna take a 3 by 3 matrix to prove it, right? And you can generalize it to anything. So in a 3 by 3 matrix, can you tell me what elements, let's say there's no row exchanges. In a 3 by 3 matrices, what elements do I need to eliminate on row 3? The element A3, 1, and then what? A3, 2. All right, so I am going to try to write down a formula for the third row of this upper triangular matrix U. Okay? So it says row 3 of U. Remember how we're going to get the row 3, right? So the row 3 of U is my original matrix A, all right? And then I'm going to do some linear operations between rows. So to get rid of the element A31, what did I do? I took the multiplier L31, and I subtracted L31 times row 1 of U from row 3 of A. And you notice I say I subtracted row 1 of U, okay? Because U is whatever matrix is already there, that's what I have to use, okay? And here I have L32 times row 2 of U. So if I take this equation and I rewrite it, it says row 3 of A is L31 times the row 1 of U, L32 times the row 2 of U, and 1 times the row 3 of U. So you know what that is? It's nothing else but basically the product, the third row of L times U. Right? So basically the matrix cell has, if you look at row 3, it basically has the element L31, L32, and 1. Okay? You can, again, practice with a 3 by 3 matrix to convince yourselves that this is the case. The bottom line that I want you to remember and never to forget is that when you look at these inverses of the elimination matrices, when you multiply them and you compute this matrix cell, it's basically the unit matrix and the multipliers below the diagonal, directly below the multipliers. So, I mean, the diagonals. So if you know the multipliers, you can immediately write down what L is. All right. So actually, I don't need this example. Let me see, what slide? Is that 37? So I need to jump somewhere. I need to go to slide 39. So let me give you a slightly different decomposition that very famous in linear algebra. When you play with computers and you solve equations, this comes often. So remember, So we wrote the matrix A as L times U. And the diagonal elements of L are what do I have in the diagonal elements of L? 1, right? So the diagonal elements of L are 1. What do I have in the diagonal elements of U? How do we call those elements in the diagonal elements of U? The pivot elements. So some people will say, wouldn't it be nice if U also had 1 in the diagonal so it can look like L, you know? And the answer is, yeah, I can do this, no big deal. And the way you do this, you can write U as this matrix where you take the diagonal elements and you multiply them on the left or the right with this diagonal matrix D1, D2, Dn, where these are the pivot elements, okay? So this decomposition then becomes, instead of the original LU, now it becomes L times D times U, and I have not changed the notation for U because in the literature, this is how it comes, right? So when you see a decomposition that looks like this, it is really the LU decomposition. It simply implies that instead of having the pivots on the matrix U, you now have 1s, all right? Nothing else. It's really, again, part of the LU decomposition. Okay, so why do we care about the LU decomposition and why this is very powerful and way better than computing the elimination matrix? Because at the end of the day, solving AX equal B becomes the following problem. So you remember we have AX equal to B, and A became L times U. So can I take this system of equations, LU times X equal to B, and split it in two systems of equations? I can call UX equal to C, and then this equation, the AX equal to B, becomes L times C equal to B. You agree? Look at those. Basically, AX equal to B became two simple systems of equations. And why do I call them simple? What is particular with these systems of equations? Why are they simple? Because L is what matrix? Is lower diagonal, so you can actually solve LC equal to B by what? If I give you a matrix that's lower triangular times L times C equal to B, what is the procedure to solve it? If it's lower triangular. How do we call it? Can only be this way or that way. So it's that way, all right. So now that's how I communicate with my class, okay? This way or that way. So what way? That way, which we call it what? It's a forward type of calculation, okay? So L times C equal to B, it's computed with a forward calculation starting basically from C1, then C2, C3 to Cn. And UX equal to C is computed what? I have now an upper triangular. So I'm starting from the bottom, right? I can compute xn, then xn minus 1, and go all the way up. So that is with back substitution. And I can tell you, and I'm going to give you the number shortly, the cost actually for, if you have large-scale matrices, go from the order of n cubed, where n is the order of the matrix, to n squared to do this type of calculations. So you really, without this type of decomposition, there is no way you can do calculations with matrices of order 1,000,000 the way you will have in numerical simulations, let's say in fluids or solids or things like that. So I have a trivial example. If you want to solve this 2 by 2 times x equal to that, you can immediately see that the LU decomposition is this L, this is U. So you solve LC equal to B with forward calculations. So you can immediately compute C1 from the first row, then you can substitute in the second row and get C2. And UX equal to C, you can immediately appreciate that you can calculate with back substitution to find what you really care, which is this vector X. Okay. Don't have a lot of times, and I don't want to give you a headache. In this slide, there is a calculation of how much it costs to do actually the LU decomposition. And it actually will be a very nice homework exercise. So unless I forget about it, I can give you to do all the details for me. But if you think about it, right? If you start, with, row 1, you keep it as this, and then you say, I'm going to get rid of A21. So what you need to do is you need to multiply the first row, which is n elements, by the multiplier, and then you need to subtract it from the second row. How many calculations is that? I mean, approximately, right? So if I look at one row, the second row, I'm going to have to multiply the first row by the multiplier. How many multiplications I have to do for an n by n matrix? N, all right? And then I'm going to have to subtract. But then you will have to do the same thing for the third row, the fourth row, the last row, okay? So obviously this looks like an n squared type of calculation. Not precisely, but n squared, because you have to do n multiplications for each row, and then you have to do this for n rows, so n squared. So if you do the calculations basically for the elimination, it comes up that you need n cubed over 3 multiplications and n cubed over 3 subtractions. So if n is 1,000,000, this is a very expensive proposition. And as I mentioned, for this upper and lower triangular systems with forward and backward substitution, the number of multiplications and subtractions that you need is n squared. So really the cost, it is the elimination that is n cubed over 3. Okay, the elimination is n cubed over 3. Now, let me actually, when you do large-scale simulations, you'd be surprised. I mean, you write a large finite element code, you spend lots of times debugging and this and that. At the end of the day, all the cost goes in solving AX equal B. That's why linear algebra is the most important subject. Okay? Literally, all the cost goes in solving AX equal to B. Now, the good news is, if somehow the matrix that you try to do LU decomposition is banded, and a banded matrix means it's only non-zero around the diagonal. And half of the width is called the bandwidth of that matrix. And when you do finite elements, for example, all the matrices are banded because the interactions are local, okay? So if you have a banded matrix with W non-zero elements below and above the diagonal, it comes out that the elimination cost drops down to n times W squared, and this forward and back substitution, it drops down to 2 times NW. And if it happens, so basically we went from n cubed and n squared to W squared and W type of cost. And if you have a 3 diagonal matrix, so if somehow your problem gives you a 3 diagonal matrix, so there is only one line above your diagonal and one below, the cost actually of elimination and solving AX equal B is proportional to n and 2n. That's very fast. All right? That's why numerical software that somehow takes advantage of a banded structure where the matrices look like this, you see the reason, okay? So when you do finite elements and you number your nodes, it has to be such that somehow that you can get as minimum bandwidth as possible, because solving AX equal to B, it is a trivial affair. Unfortunately, I would not be able to do anything I wanted today, which is to finish this lecture. So let me jump on this 1 second. So how does the decomposition A equal LU looks if I do row exchanges? Instead of having A equal LU, you now have P times A equal LU, where this matrix P is what? That will allow to do a row exchange. How did you call this matrix from lecture 4 that allows you to exchange rows? The permutation matrix. All right? So the idea is exactly the same. You know, if somehow, let's say this is my matrix A and that element is 0, I'm going to exchange row 1 and row 2 using this permutation matrix, and then I'm going to do an LU factorization on the matrix P times A. All right, so when you have these exchanges, you use P times A as equal to LU. And let me see slide 48. Now, let me make it a little bit more sophisticated for you, and then we will finish because it's 11:12. A lot of times, when you do calculations, rather than having numbers in the matrices, you actually have bunch of matrices. So in this case, I write A as this block of 4 matrices, okay, where A11, A12, A21, A22 are matrices. Matrices. This is very common. They're matrices. What you learn about elimination, you can actually do it in this matrix of matrices. So for example, the elimination matrix will have to get rid of this matrix A21. And how do you get rid? You actually have to find the pivot. And what's the pivot? A21 times A11 inverse. Okay? And because I'm going to subtract that times the first row, you're going to have to put a minus sign. And you can check that this matrix times that is equal to this. And this formula has lots of applications in numerical simulations and calculations. And it goes under the name of what is called the Schur Complement. Okay, so I am going to stop there because I can hear some screaming outside the door of students eager to come for a lecture. Do me a favor, go to office hours, including today, and send me an email on what is going on, because I don't see my TAs often or at all. So I want to know that there is some help that you're getting with the homework. Okay, so I'll see you on Friday.